Welcome to all. Our today's topic is transport phenomena, viscosity of gas. In this topic, it contains the following points. Introduction about the equilibrium state of gas, transport of momentum, derivation for coefficient of viscosity, and factors affecting on coefficient of viscosity, that is dependence of temperature and pressure on viscosity of gas. Here we explain the equilibrium and non-equilibrium state of gas. The gas is said to be equilibrium if its behavior is steady with time. It means no net changes can occur in a gas system. Equilibrium state, when gets disturbed due to external action like mass motion or flow velocity, or addition of the heat, or addition of gas to a gas system, the state becomes non-equilibrium. In non-equilibrium state of gas, the different part of gas have different velocities. This is due to mass motion or flow velocity. Different part of gas has different temperature. This is due to addition of heat. Similarly, different part of gas have different concentration due to addition of small amount of gas to a gas system. Means in non-equilibrium state, different layer of gas has different velocities, temperature and concentration. In such a non-equilibrium state, the physical quantity like momentum, energy and the mass transport from high gas level to low gas level so as to bring the equilibrium state. In equilibrium state, the total physical quantity transported across the unit area is zero due to equal flow in opposite direction. Using that concept, we explain the next term. To explain transport phenomena, here we imagine gas molecule treated as a vehicle. Since the vehicle can carry the heavy load from one place to another place, in the same manner, gas molecule also transport the physical quantities from one region of gas to another region of gas. This phenomena is known as transport phenomena. Here we explain the three phenomena: viscosity of gas, thermal conduction and diffusion. Using these different regions of gas, to explain the viscosity phenomena, different part of gas or different region of gas may have different velocities. Then there will be relative motion between the different layer of gas with respect to one another. In such a case, the faster moving layer, whose velocity is v plus dv, import momentum to the slower moving layer, whose velocity is v minus dv or v, so as to bring equilibrium state. This gives rise to phenomenon of viscosity, and it is a result of transport of momentum. In the second case, thermal conduction, if the temperature of gas in different region is not uniform, it means the topmost layer is a hot region, lowest region is the cold region, has topmost hot region highest temperature, cold region which having the lowest temperature. Due to temperature difference between the neighboring layers, temperature gradient is established, and the energy can be carried from the region of higher temperature to the region of lower temperature, so as to bring equilibrium state. This gives rise to conduction phenomena, and it is a result of transport of energy. In the third case, diffusion of gas, if the molecular density or concentration of gas is not same throughout the region, uppermost region has higher concentration in comparison with the lowest region of gas, and due to difference in the concentration between the different layers, concentration gradient is established, and the mass of gas can diffuse from higher concentration to lower concentration, so as to bring the equilibrium state. This is a phenomena of diffusion, and it is a result of transport of mass. Hence, the viscosity, conduction, diffusion are due to transport of momentum, energy, and mass respectively. These known as transport phenomena. Under transport of momentum, here we derive an expression for the coefficient of viscosity of gas. For that purpose, we use different layer of gas moves with different velocity. In this diagram, we use a one intermediate layer which called as a reference plane or layer A. Above the layer A, there is another layer B, and below the layer A, the layer C. All layers are parallel to each other. Here we assume that the gas flows in fixed horizontal surface OX, that is in the XY plane. The velocity of the gas layer in contact with OX is 0, and it increases along positive Z direction. Here, the velocity of this reference plane is V, and the velocity gradient is dV by dz. Here we assume that all gas layers which are at a distance equal to lambda, only that gas molecule in that this layer can cross the unit area of the layer A in both directions, vertically as well as downward. Suppose the all layers above A are moving faster than all layers below A, while all layers below C moves slower than all layers above A. The faster moving molecule exert a tangential force on this layer A, and it tends to increase its velocity. At the same time, the slower moving molecule also exert equal force in opposite direction so as to decrease its velocity, and therefore the velocity tangential force is set up between the layers. That tangential this force try to reduce the difference in velocities of the layers on the two sides of the layer A. This property is known as viscosity of gas. Here, the velocity gradient over the distance lambda is lambda dv by dz, where lambda is the mean free path. Therefore, the velocity of the different layer, we write the velocity of the layer is v, velocity of the layer B is v plus lambda dv by dz, velocity of the layer C is v minus lambda dv by dz. According to theory of viscosity of gas, the viscous force per unit area of the layer A is F, and it is given by the relation eta dv by dz, where eta is the coefficient of viscosity of gas. Here, due to thermal agitation, all gas molecules are in the random motion. Suppose we choose n number of molecules per unit volume of gas, and these number of gas molecules are moving along each of three axes. Hence, the n by 3 number of molecules are moving along each axis and along any one direction. That direction is upward or downward. That number of molecules moves with average velocity c bar. Hence, the total term we just take into consideration. N by 3 is the number of molecules are moving along each axis. Multiplied by half means these number of molecules moving along any one direction on each axis. Multiplied by c bar, this n c bar divided by 6 gives the number of molecules crossing the unit area of the layer A in the unit at this time in upward or downward direction. Here we calculate the momentum carried by the molecule B towards the layer A. Similarly, the momentum carried by the molecule C towards the layer A in upward direction, as well as here this. from B to A in the downward direction. Once we calculate the momentum, we must know that what is the velocity of the molecule in the layer B and what is the velocity of the molecules in the layer ABC. Hence, to calculate the net transport of momentum across the layer A, the momentum carried by the molecule in the layer B to cross the unit area of the layer A in unit second from above in the downward direction is given by the equation mn c bar by 6 into v plus lambda dv by dz. In that equation, represent the momentum since mass into velocity of number of molecules. Velocity of v plus lambda dv by dz is the velocity of the gas molecule in the layer B. That velocity is in the, we write here, once they cross the unit area of the layer A in the downward direction, we have to multiply it by mass into number of molecules. It gives the total term momentum carried by the molecules in the layer B once they cross the unit area of the layer A in the unit time in the downward direction. In the same manner, we calculate the momentum carried by the molecules in the layer C. Layer C is the below the layer A. Therefore, the number of molecules in the layer C will cross the unit area of the layer A in the unit time from below in upward direction. Now that time we just note here what is the velocity of the molecule in the layer C, the number of molecules who moves with average velocity c bar multiplied by mass. The total term is momentum. In the equation we write as mass into velocity multiplied by number of molecules. M n c bar by 6 into v minus lambda dv by dz, where v minus lambda dv by dz is the velocity of the molecule in the layer C. They cross the unit area of the layer A in the upward direction. Hence, it is represented by the equation 3. Once we know the momentum carried by the molecule B in the downward direction, similarly momentum carried by the molecule C in the upward direction to cross the unit area of the layer A in both cases. Therefore, what is the net transport of momentum per unit area per second of the layer A? That term we determine from the equation 2 and 3. Get the difference of the two equations. And it is mn c bar by 6 into bracket v plus lambda dv by dz minus v minus lambda dv by dz. Now simplify this internal bracket term. Here v cancel, plus lambda dv by dz minus plus lambda dv by dz, it is twice, and therefore the term becomes mn c bar by 6 into 2 lambda dv by dz. Simplify again, mn c bar by 3 into lambda dv by dz, and it gives the rate of change of momentum or force per unit area. Hence, according to the Newton's law of motion, we know the rate of change of momentum is nothing but force per unit area. According to earlier case, equation 1, the theory of viscosity of gas, the viscous force per unit area given by eta dv by dz, that term is exactly same as the net transfer of momentum per unit area per second. Hence, we equate the equation 1 and 3 and we write the equation eta dv by dz is equal to mn c bar by 3 into lambda dv by dz. Cancel dv by dz on both sides and rewrite the equation eta is equal to mn c bar by 3 into lambda. Here, mass into number of molecules, that gives density of gas. Hence, in terms of density of gas, the coefficient of viscosity is written as 1/3 rho c bar lambda. Equation A is the required expression for the coefficient of viscosity of gas. Here we interpret that this term. In that equation, the density of gas is constant. Lambda mean free path is also constant. Therefore, the coefficient of viscosity is directly proportional to the average velocity of the gas molecule. From that equation, it is also possible to estimate diameter, molecular diameter, and mean free path of the gas molecule. That equation we simplify. As you know, lambda is equal to 1 divided by pi sigma square n. Therefore, eta is equal to 1/3 m n c bar into 1 divided by pi sigma square n. Therefore, sigma square we separate from that equation and rewrite mc bar divided by 3 pi eta, or sigma is equal to mc bar under root mc bar divided by 3 pi eta. If we find directly the mean free path, then the lambda is equal to 3 eta divided by rho c bar. From the mean free path is also estimated from that equation, as we know the viscosity and density of the gas. Nextly, we explain the factors affecting on viscosity of gas. The first this term we discuss here, the dependence of temperature on viscosity of gas, how the temperature depends on viscosity of gas. The equation known to you, eta is equal to 1/3 rho c bar lambda. Here all terms except c bar constant. Here rho is constant, lambda is constant. Only c bar is variable term. Hence, coefficient of viscosity depends on average velocity of gas molecule. But according to the kinetic theory, average velocity of gas molecule is directly proportional to square root of absolute temperature, as c bar is directly proportional to root T, then eta also directly proportional to square root of absolute temperature. Hence, coefficient of viscosity depends on temperature and it varies, like eta is the linear variation of square root of absolute temperature. Second term, how the pressure depends on viscosity of gas. That term we also explaining here. At constant temperature, the root we say the average velocity of gas molecule is independent of pressure. Means what is the density of gas on effect of the pressure? The density of gas increases with pressure, but mean free path decreases in the same ratio. Hence, we take the product rho lambda, one term increase, other term decrease, so the product tends to remain constant. And if the rho lambda term is constant and c bar is, we see here the average, here the velocity, it is independent on the pressure. Hence, coefficient of viscosity totally independent on pressure. And that is the term coefficient of viscosity, transport of momentum. Under that term, we derive coefficient of viscosity of gas and what are the factors affecting on viscosity that we have to discuss here. Thank you.